Hello, statistics scholars. Happy Saturday. It's me, Dr. McNeil. It's Saturday, November 8th, about 1:30. I hope you're having a great weekend. I hope you are also planning to enjoy the long weekend because we don't have class on Tuesday because of Veterans Day. Today, my goal is to create a video. I'm going to create a video in three parts. I want to accomplish these three things. One, I want to talk about the standard error and illustrate the difference of the standard error over the three t-tests that we've been studying in this first unit in our inferential statistics module. One sample, paired sample, and independent sample t-tests. I want to highlight and confirm, solidify for you what the standard error is. The standard error sounds like something's wrong, something, it's an error, but it's not an error at all. The standard error is a value, a number that we get that tells us that if we continue taking the same number of sample from the same population into infinity, how much likely is the mean going to change? So in essence, what it's telling us is how stable the mean is as an estimator of the true population mean. And what we really want is a standard error that's very small, because if the standard error is large, that means every time we take a sample, the mean's going to move around a lot, which means it's not very reliable in terms of predicting or estimating the true value of the population mean. All right, so that happens very different. There's different notations, there's different formulas, but they're essentially doing the same thing. Two, I want to go over one of the problems in chapter 10, item 4. A couple of you have reached out because you're a little confused about that. I understand how that goes. When we're in class, it's easy to follow along. You have your peers around, but sometimes when you get home, some of the concepts aren't as clear. So I want to make sure that I illustrate that because we're wrapping up this week our last t-test, the independent samples, and then we're moving into ANOVA. I'll create a different video for that. And the third thing I want to accomplish, a lot of you were sort of asking about this because I wrote it on the board on Thursday. The full formula or the full decision for whether you're rejecting or failing to reject the null hypothesis, there's a structure that I want you to use. You may notice, a few of you, that even though your chapter exercises seem very complete, I mark them incomplete. I want you to take a look at my note, and all I'm really saying is for the questions in the chapter that require you to make a decision, I want you to write out the full decision. And so I'm going to go over the decision, the format for one sample, paired sample, and independent sample, so that you have something that you can refer back to. All right, let's start with the standard error, how it's different, and really how it's the same. Let's head over to the map. Okay. We have three t-tests. We have a one sample. We're testing our sample against a assumed or given population mean. We have a paired sample, which we are measuring two different times, time one and time two, and looking at the difference. Either there's an increase or a decrease. And we also have independent sample t-tests. And they all use the standard error. Remember, the standard error tells us how accurate and stable the sample mean that we got is in terms of an estimator of the true value in the population mean. So let's talk about the notation. The notation for a one sample mean for the standard error is SM. The notation for a paired sample is SMD because we're looking for the difference. And the notation for an independent sample is M1 minus M2. So this is the standard error. This This is the standard error of the mean difference, and this is the standard error, the difference between group 1 and group 2. The formula is quite simple. It's just the standard deviation divided by the square root of n. So if the standard deviation is 15, let's say, and n is 10, so it's the square root of 10. Oftentimes, I think some of you get a little wigged out when you see the square root as the denominator. It's not that hard, especially if you have the calculator. So we would enter 15 divided by, and then we invoke the square root, which is second and square. It gives us one parentheses already. That's been a source of confusion. You don't need anything when you're just getting the square root. So I'm just going to enter 10. And when I hit enter, it's going to tell me what it is. 4.734, which is 4.74, which isn't a very stable standard error, which means it could go 4 points lower or 4 points higher. That sample mean is going to bounce around quite a lot. But I just wanted you to see the formula and how to key it into the calculator. The formula for a paired sample standard deviation, or the standard error of the mean difference, is, instead of standard deviation, it's the standard deviation difference. Because what we've done is taken the difference between time 1 and time 2. If we're looking for an increase in scores like pre-test and post-test, where we want the scores to go up in time 2, the formula for the difference is time 2 minus time 1. But if we're looking for a decrease, let's say we are doing a clinical trial and we want a decrease in symptoms, so we measure people at the beginning, we give them the treatment and measure them at the end, so we want the scores to go down. So that formula is T1 minus T2. But whatever we're doing, we're using now the difference. And now when we get the standard deviation, that standard deviation is the standard deviation difference. That mean is the mean difference. So standard deviation difference divided by the square root of n, still the same. So I'm not going to do it because it's really the same thing. But here in the independent sample, because we're looking at two different groups that are independent of each other, they may not have the same n size. So we have to pool them together so that they are equal. We put them on an equal scale. So the formula is a little different. It's called the pooled variance divided by n1, or the first group, plus the pooled variance divided by n2. We just add these two together and we get the square root of all of that. But if you look at what's really happening, we have a square root over n, square root over n. Here we have n, this is still n, just n of one group and n of the other group. But now the square root line is also including the numerator and not just the denominator. Now that might look a little weird, but it's not that weird. All we're really doing is getting the standard deviation, just like we did here for one sample and for paired sample. And we're accomplishing this by this little thing. I call it sort of statistical gymnastics. So we take a look at how we normally get from sum of squares to variance to standard deviation. The formula for that really is, we haven't been looking at the formula much, but I want you to see that you really do understand the formula because you understand the steps. It's the sum of all the x's minus m squared. I'm going to put this little I here. I means all the individual all the individual x's. So when we're getting the sum of squares, we take x, we add it up, we get the average of x, we go to the absolute deviations, we subtract the average, sorry, we get x, we get the sum of x, we get the average of x, or the mean of x. Then we go to the absolute deviations, we subtract the mean from every x, and we add them all up, they equal 0. Then we go to the squared deviations. We take every absolute deviation, and square. When we add those all up, that equals the sum of squares. That's this formula. Every x minus m, all of them squared. Now, to get from the sum of squares to the variance, which is, this is the formula for variance. Look at that. That looks like variance. Variance, variance. All we're doing is taking the sum of squares, which is this formula. I'm not going to write the formula over again. I'm just going to use the notation, divided by n minus 1. And we're doing that because it's a sample. But really, all this really is if sum of squares is all of the deviations minus the mean, because we took the mean out, it is the average of all the deviations. A little more than the average because we took one away. But this looks just like x minus n is the mean, right? We're dividing it by n. We're just dividing it by 1 less than n. And then to get to the standard deviation, we take the square root of the variance, right? Take a look over here. That's just right there. The only difference between this and that is that it's pooled. So hopefully that freaks you out less, helps you understand that all we're doing really is by including the square root line, we're just including the variance, although it's pooled, as the square root. And when you square root the variance, that's the standard deviation. Just like that numerator is for the one sample, the standard deviation difference for the paired sample. And so that's how we get the standard deviation for the independent sample. All right? Hopefully that makes sense. Let me show you how that works by working through at least one of the problems in chapter 10, number 4. See you over there in a second. All right, so let's take a look at our chapter 10 exercises. To remind you again that the chapter 10 exercises, well, in the whole book really, every odd number, they give you the answer, which I think is a good way to test your knowledge because you could work on the problem, do what you think, and then go take a look at the answer and check. That gives you some, I don't know, confidence to be able to tackle the next one. We went over item number 4, which has an A, B, and C in class, but maybe you didn't quite get it, and I'm going to illustrate that. I'm going to show you with the calculator really what's happening. Not that hard, but it can feel a little, I don't know, confusing. So a lot of what we're going to be doing in this second half really does involve your calculator. Many of you have calculators. I'm surprised that some of you didn't. I still have calculators. If you need one, I recommend that you get one. A few of you have your own calculator, and I've been really impressed by how you've handled making the changes of the calculations for your calculator, because every calculator works a little bit differently, and I would know or have the time really to figure out how your calculator handles data and all that, but you've done a fine job doing that. So I'm just going to transpose what's happening in A. In A, they gave us a standard deviation for group 1, which was 24. They gave us a standard deviation for group 2, which is 21. They told us that the n size for group 1 is 36, and the n size for group 2 is 49. All right? So all they're asking us, or what they're asking us to do, is to calculate the standard error. So let me remind you the standard error formula. Standard error, square root of the pooled variance divided by n1 plus the pooled variance divided by n2. All right. Which reminds us that we need the pooled variance. We don't have variances. We don't have sum of squares because the formula for variance, the pooled variance, is sum of squares 1 plus sum of squares 2 divided by degrees of freedom 1 plus degrees of freedom 2. That's the formula over there. But we don't have sums of squares, but we do have standard deviations. If we have the standard deviation, we could work backwards. By squaring the deviation, we get the variance. And by multiplying by the degrees of freedom, we get the sum of squares. So all we have to do is reverse engineer. We have to remember that if n is 36, degrees of freedom is 35. And if n2 is 49, then the degrees of freedom 2 is 48. Okay, so we need to get the pooled variance so that we can plug it in here. I'll do that over here. So keep in mind, we start with 24, and then square it. That's what we just done there, right? And make sure you can see the calculator, 24 squared. And then we multiply it by 35. So the sum of squares for 1, sum of squares 1, is 20,160. Now we need the sum of square for the second sample. That's 21 squared times not 49, but 48. That gives us 21,168. That's simple enough. We just have to add those together. And if we put parentheses around them when we do that, the calculator will handle the numerator. Now let's just put down as the denominator, degrees of freedom 1 plus degrees of freedom 2. We're just following this recipe right here, right? So degrees of freedom 1 is 35, and degrees of freedom 2 is 48. And that's the denominator. We just need to add those together. So if we put parentheses around the numerator, put parentheses around the denominator when we're calculating those sums, it's going to tell us what the pooled variance is. So left parentheses, 20,160 plus 21,168, right parentheses, and you can see there's a parenthesis. So it's going to do that first, and then we're going to ask it to divide whatever the sum. We'll start again with the left parenthesis, the sum of 35 plus 48. All right, so we get 497.927. 927 means we rounded up to 93. 497.93. Perfect. So that's now the pooled variance. We figured that out. Now we just have to plug in the pooled variance here and here, and plug in not the degrees of freedom, but actually the n size, 36 and 49, and plug that in here. And now that will give us the standard error of the difference between group 1 and group 2. So 497.93 divided by 36, which is n1, plus 497.93 divided by 49. And whatever that is gives us the standard error of the difference between M1 and M2. And remember, all we're doing is stretching the square root bar to include the numerator as well. But we have another little problem is we want to get the quotient of this, whatever this is, and whatever this is, add them together and get the square root. So I'm going to do it the long way first so that you see what's happening, because I don't want you to be mystified, but I want to demystify it. So let me get the quotient of 497.93 divided by 36. 497.93 divided by 36. equals 13.831. We can leave it at 83. Plus, let's figure out what 497.93 divided by 49. 497.93 divided by 49 is 10.161, which we can just leave it to 10.16. And these two together, 13.83 plus 10.16 equals 23.99. Okay, that's fine. Now let's see what the square root of 23.99 is. We simplified that, right? By doing these calculations separately, adding them together, and now finding out what the square root of that is. But even before we do it, we can kind of figure out where it's going to be. So it will be more than 4 squared because 4 squared is 16. It'll be less than 5 squared because 5 squared is 25. We're looking at 23.99. So it's going to be 4 something something. So the square root of 23.99, it is 4.897, 4.897, which we can round up to 490. Because the 7 makes us go 1 more up, and we're already at 89, so we go to 90. See that? 4.897, so 4.90. Now let's do all of that without breaking it down. Let's just do the square root and put parentheses around both of those numbers and have the have the computer or the calculator, which is a computer, do that. So square root. Okay. Now, this is a thing that happened, I think, in class a couple of times. You see one parentheses there and you think, oh, I don't need one. That parentheses is always there. So we actually need a parentheses to initiate this number. So we want that calculation. 497.93 divided by 36 and right parentheses. So now we have that handled. Plus, now we need another parentheses. 497.93 divided by 49, and then the right parentheses. Now, when I hit enter, we should get 4.90. There might be a rounding error, but yeah, 4.898, which is 4.90. All right, hopefully that gives you enough courage and confidence to try B and C by simply following the steps that I outlined. I would recommend sort of writing out the way that I wrote it and go for it. I don't really mind that you make mistakes. I just want you to go for it. I want you to try it because confusion and mistakes come right before you figure it out. So you have to be willing to make mistakes. All right. So that's the second thing that I wanted to accomplish. The third thing is working through the full decision. I'm going to show you the 3 types of decisions, one for one sample, one for paired sample, and the other for independent samples. Let's take a look at that. All right, so let's take a look at t-test decisions, the correct version. I'm really teaching you what's called the APA or American Psychological Association. We're on the 7th edition of that. That changed about, I think it was 2020 when it changed. I remember APA 6th edition. But here are the rules. Let's take a look. So when you're taking a one paired versus a paired versus one sample versus a paired versus an independent sample t-test, pretty much the structure is the same. I'm going to show you what we do when we're rejecting the null hypothesis versus failing to reject the null hypothesis and what gets changed depending on the test. So For one sample t-test, based on the data collected, we give the n size, we give the mean size, and we give the standard deviation. Notice that standard deviation, when we're writing it out, is actually SD. And it's all italicized. N is italic, M is italic, and SD. That's because we're using them as notation for statistics. There is or there isn't, depending on what the situation dictates, there is or isn't sufficient evidence to reject the null hypothesis. A one sample t-test revealed that the effect was either small, moderate, or large. See that right here. I was trying to find my pen. There we go. Right here, small, moderate, or large. And then we give the t-test itself, and degrees of freedom is in parentheses is what we write. So remember the actual degrees of freedom that we use. So if we're looking for 34, for instance, 34 degrees of freedom may not be on the chart, but 30 is. So you would type in, or you would write 30. And then the actual test result, the t obtained. And then p is less than 0.005 if we are rejecting the null hypothesis, and it's more than, let me fix that. You're getting me to see me do something kind of as it's happening. Fix that. Equal 0.05. Depending on what our alpha is, most of the time we are using an alpha of 0.5. There might be a few times that we use an alpha of 0.1, but that's not generally the case. All right, so I'll just fix that. Let's take a quick look at it again. So if we're rejecting the null hypothesis, then P is less than. If we're failing to reject it, it's greater than. And 0.05 or whatever the alpha is, then we give whatever the Cohen's d result is, and then 95% confidence interval and the lower number and the upper number. That's the basic structure. For a paired sample, it looks very much the same, except now we're talking about the difference. So based on the data collected, n still is whatever the n size is, but now mean is mean difference. And the difference is a subscript. And standard deviation difference is a subscript. There is or isn't, just like before. Everything else follows suit. The small, moderate, or large, depending on what the result was. The degrees of freedom in parentheses, less than or greater than, if we're rejecting or failing to reject the null hypothesis, the Cohen's d value, and the 95% confidence interval, lower and upper. For independent sample t-test, now we have to blow it out because we're looking at two different samples based on the sample collected from sample name 1, N1, X, M1, X, SD1. So we're giving the descriptive statistics for the first sample, and now see we're doing it differently, or labeling it differently for the second sample. Again, there is or there isn't sufficient evidence. A paired sample t-test. Here we said, oops, I did that again. It is not a paired sample, but an independent sample. Let me highlight that for you. Here we're talking about a one sample. Here we're talking about a pair sample. And here we're talking about an independent sample. But everything else pretty much is the same. Even had to correct a couple things. All right. Hopefully that gives you some clarity about the three things. First, about how the standard error changes from one sample, paired sample, and independent. How we can lift the standard error of the mean difference from just the statistics, the descriptive statistics like the standard deviation by reverse engineering it, introducing remembering the point of the pooled variance by pulling the square root bar all the way up to include the numerator as well. And then I just gave you an outline of writing the full description of the decision. All right, hopefully that gave you everything you needed to feel confident as you wrap up independent sample t-test. My next video will be working through an ANOVA. I'm going to sort of give you a brief overview of ANOVAs and also work through the one problem in ANOVA that I think will give you some challenges because you have to actually do all the tedious calculations. All right, see you soon.